The paper of the day is Access Path Selection in a Relational Database Management System. System R was a very influential relational database management system built at the IBM San Jose Research Laboratory starting in 1975. This paper introduces the idea of query optimizer built as part of System R that plans the most efficient way to retrieve the data requested by a SQL query, as well as giving insight into how a query optimizer may be constructed. The paper also quietly introduced the important result that a declarative query language can be supported with no loss of performance compared to the more common procedural query language approaches of the day. So here's the abstract of the paper. In a high level, query and data manipulation language such as SQL requests are stated non-procedurally without reference to access path. The paper describes how System R chooses access paths for both simple, that is single relation, and complex queries such as joins, given a user specification of desired data as a Boolean expression of predicates. System R is an experimental database management system developed to carry out research on the relational model of data. System R was designed and built by members of the IBM San Jose Research Laboratory. Highlights: the 4 phases of SQL statement processing in System R are parsing, optimization, code generation, and execution. We are concerned here with the optimization phase, and in particular with access path selection. An access path is a way of accessing the tuples of a relation. There is always the possibility of full segment scan, but there may also be one or more indices. Now, scan and access paths. A scan returns a tuple at a time along with a given access path. Next is called to retrieve the next tuple. For a segment scan, System R looks at all segments which contain tuples from any relations and return those tuples belonging to the given relations. Segments in System R may help tuples from multiple relations. All the non-empty pages of a segment will be touched. However, each page is touched only once. In contrast, when an entire relation is examined by an index scan, each page of the index is touched only once, but a data page may be examined more than once if it has 2 tuples on it which are not closed in the index ordering. Index scan also have the advantage that they need not scan the entire relation. For example, starting and stopping key values may have been specified in the query. A query may specify predicates that apply to a tuple to determine whether or not to be included in the result set. In System R, the set of predicates are known as search arguments, or SARGs in short, and these are expressed as a Boolean expression in disjunctive normal form. Each individual predicate is of the form called comparison operator value. Selinger et al. Started with the case of query involving only one relation and then later built on this to show how queries involving multiple relations can be optimized. The query optimizer looks at the 4 key pieces of information: the predicates in the query, the access path available on the relations referenced in the query, statistics that are maintained on relations and access paths, and the desired output ordering, if any. That is an ordered by or group by clause. A cost prediction is made for each access path, which is based on the amount of expected I/O, that is page fetches, and CPU utilization, denoted as RSI calls in the paper, which is the predicted number of tuples returned from the underlying storage system. A weighting factor W enables adjustment of the cost balance between I/O and CPU. So cost is equal to cost of I/O plus weight multiplied by cost of CPU, where cost I/O is number of page fetches and cost CPU is number of RSI calls. For a relation T, the System R maintains the following statistics: tuples T, the cardinality of the relation; pages T, the number of pages in the segment that holds the tuples of relation T; page ratio is the fraction of data pages in the segment that holds tuples of the relation. So page ratio T is equal to pages of tuple T divided by number of pages in the segment. And for an index I, keys I equal to number of distinct keys in the index, and I pages equal to number of pages in index I. Joins. Given a way to estimate the cost for queries involving a single relation, we can extend it to estimate the cost for different approaches to joins. We can first consider a join of 2 relations and then generalize to n-way joins, which can be visualized as a sequence of 2-way joins. Selinger et al. Considered nested loop join based joins and merging scan based on joins. In a nested loop join, the outer relation is scanned, and for each tuple retrieved from the outer relation, the inner relation is scanned to retrieve all the tuples which satisfy the join predicate. In a merging scan, the outer and inner relations are first sorted in join column order. So columns of equijoin predicates are also defined in interesting order so that they can subsequently be more efficiently merged. The key question here is what order relations should be joined. For a 2-way join, which is the inner and which is the outer relation with n relations in a from list, where there are n factorial permutations to consider. find the optimal plan for join operations, a tree of possible solutions is constructed. The cost of a join is computed based on the costs of scan and for each relations and the cardinalities. Let C outer path 1 be the cost of scanning the outer relation by path 1. Let n be the cardinality of the outer relation tuples satisfying the applicable predicates, where n equal to product of tuples of for all t of the join so far multiplied by product of the selectivity factor for all the applicable predicates. Let C inner path 2 be the cost of scanning the inner relation satisfying all applicable predicates. Then the cost of a nested loop join is C outer path 1 plus n multiplied by C inner path 2, and the cost of the merge scan join is the cost of actually doing the merging plus the cost of sorting the outer or inner relations if required. Nested queries. For example, select name from employee where salary equal to select average salary from employee. If the nested query does not reference a value obtained from a higher level query block, then it needs to be evaluated only once. In this case, the optimizer will evaluate the subquery first. If the nested query references a value from a higher level query block, then in principle it needs to re-evaluate it for each candidate tuple from the referenced higher block. Let's look at the overall contributions of the paper. This paper did address the issues of access path selection for queries, retrieval of data manipulation, that is update and delete is treated similarly.